Welcome to the fourth lecture of the Varahamihira Science Forum. The speaker of this month is Siddharth Chandrasekar. The topic is Issac Newton and his most famous scientific work, the Principia Mathematica de Naturalis, or even more later, Philosophia Principia Mathematica de Naturalis, which is effectively a book that translates to English as the Mathematical Principles of Nature. So this is we don't read the book, we read aspects of the book in our school education. Basically, when we read about the laws of gravity or the laws of motion, or even other aspects like calculus, which Newton introduced, we don't read from the original sources, but we read from condensed versions or specifically rewritten versions prepared by school committees for our school students, and that continues in a different way in college education. So, but this particular talk will focus going back to the original material, not necessarily the Latin version, but the English translation of Newton's work. There's a lot of mathematics involved in it, and the book itself has fascinated all kinds of researchers through time. I won't go into a historical analysis of it, but the context of the times. The advent of Newton marks a dramatic surge in physics. In fact, most people consider Newton as the effective founder of physics. Though not everybody does. But this particular book had a dramatic impact. And so, to know a little more about the book in detail, from the material covered in the book and the history leading up to Newton writing that book, we thought we'd have a lecture on it. Though it's a somewhat intense topic, we'll do a popular lecture, which is the fundamental idea behind the Varahamihira Science Forum. Our primary motivation is to explain a lot of science that is probably not that well covered or not covered in detail enough by speakers who can talk, proficiently on the subject, without excluding the people who are not specialists in that field. And so I think in that case, Siddharth here is an electrical engineer by profession, not a physicist. Went into photography, yoga and all that. He's a multifaceted person. He now contributes to other fields like heritage and now science. He gave a version of this talk earlier at the Madras Literary Society, which is in Egmore, which was founded about 200 years back, and which actually has a Latin edition of Newton's Principia. So that was very fascinating to have, the Latin edition at hand, or 200-year-old edition at hand while we were speaking. So today he will give us a broad overview of what Newton covered in Principia and what led him to the topics that he researched. So without further ado, here is Siddharth.
Thank you. This is the topic. I've seen this Varahamihira Science Forum, and a lot of the topics are interesting play of words. So I decided I'm going to go with the title Newton, A Force Awakens, because of the common things. And I was most influenced by the Star Wars movie A Force Awakens. But I think A Force Awakens is particularly apt for Newton, especially on multiple terms. The force that changed physics, the force that we know by his name, and multiple other phenomena that changed our perception of people, of science, etc. So, I've called this talk a peek into 17th century rational thought, because Newton actually made a very famous statement, and he said, "I stand on the shoulders of giants." And therefore, for us to start understanding who Newton is and to understand where Newton went with his discoveries, we need to understand who's the giants that he referred to. So I decided to go with a build-up of some of the epochal changes in science, starting with Aristotle, Euclid, Kepler, Galileo, Descartes, as we call it, and many Indians call Descartes. But to start with it, we will go to Aristotle. 384 to 322 BCE, Greece. most famously the student of Plato, and now even more famous, the teacher of Alexander. He actually, once Plato died, started off with Platonism, which Plato said that very famously that there are things we cannot perceive, there are things that actually are heaven sent in a certain manner. But Aristotle later discovered that that was not the approach he wanted to talk about, so he went to empiricism, which said that everything that we want to understand and everything we want to explain has to be perceived by our senses. He, as I said, was a teacher of Alexander, and his writing covered multiple subjects from physics, biology, zoology, metaphysics, logic, ethics, aesthetics, poetry, theatre, music, rhetoric, linguistics, poetry, and politics and government. Okay. Now, going from science, biology and physics all the way to rhetoric, linguistics, music, politics and government is quite a widespread, which meant that he was a man who knew what he was talking about. And he definitely came about creating the first comprehensive system of Western philosophy, as people like to call it. Unfortunately for us, only 1/3 of his work survives today. So Aristotle in one way laid the grounds for Newton. The scientists I've taken and the people I'm talking about, the giants today, are specifically related to Newton. There have been many, many more that I have not chosen. But these are the people that Newton continuously refers to, which is why I've taken them. The next is, of course, the Greek Euclid, 300 BCE. His name in Greek means renowned or glorious. He is known as the father of geometry, and Elements, which is his main work, talks about Euclidean geometry. He wrote, his main works refer to conic sections, perspectives, spherical geometry and number theory. Euclid is a very common reference we see in Newton's statements as he went on, because he used a lot of Euclidean geometry in his first set of studies. Then of course we follow on to Johannes Kepler. So in 1571 to 1630 he was a German scientist, a philosopher. He's a mathematician, astronomer, and also better known for actually being the astrologer for the Imperial Kingdom of Germany. He's actually, we know him, Johannes Kepler, because of the Kepler's laws of planetary motion, which I'm not going to get into in too much detail here. But he also did a lot of work in optics. He improved the refracting telescope, which today we know as the Keplerian telescope. He also did one thing which we don't know of, which is that he worked with an Austrian scientist called Tycho Brahe. Tycho Brahe was one of the first naked eye observers of the cosmos, made very meticulous observations. A man who was so secretive but had only one person whom he gave his observations and studies to, and that was Johannes Kepler. So here was a man who actually built upon extensive studies of naked eye astronomy and went on to move into a lot of further details. Now his book, Kepler's book, is called Astronomia Nova. If you read it, many of the modern physicists today will say, in between a lot of faff, fluff and junk, you find 3 laws of planetary motion. But we also know Kepler for a much more funny problem, which today we know as the marriage problem or the secretary problem. Because when Kepler's wife first died, he decided that he wanted to use a scientific method to select his second wife. So he set a law for himself that he was going to interview 11 women, and he had a very simple logic. He said, I will interview them. If I like them, I will say yes and there is no more interview. Otherwise I will say no and I will move on, I won't go back. So this is actually a very mathematical and statistical problem that many people quote today. However, Kepler went back on his own theory because he interviewed all 11 but came back to the 5th and married her. But anyway, moving on, we have a great that we all know of, we all quote, Galileo Galilei, Italian, father of observational astronomy, modern physics, scientific method and science. We know him more for the telescope, but we don't know him We should know him for the study of kinematics and strength of materials. He did motion of bodies, pendulums, sound, free fall of bodies. Most famously, his experiment from the Leaning Tower of Pisa that we know of, where he dropped different objects to study gravity. Though we didn't define it at that point as gravity. Then we have Descartes, René Descartes, as he is known, French philosopher, mathematician, and scientist. He is most famously known to have made his statement cogito ergo sum, which means I think and therefore I am. We know him more for his Cartesian coordinates that we use a lot in polar geometry today and all polar studies. Coordinate geometry, laws of reflection. He very famously also discovered that the angular radius of a rainbow is 42 degrees. Though I don't know how it applies to our modern science today in common understanding. Having stated all of this and where Newton came from, I decided I will take a slight deviation and go back into seeing that since we've looked at the Western thought a bit, why not look at the Eastern thought? So what happened in China? The first recorded solar eclipse in China was 2137 BCE. They found a seismological detector in 132 CE. Gunpowder was 300 CE. Block book printing was done in the 7th century CE. They found dry docks in 1088 CE. They already were fighting wars with iron-cased shells and rockets by 13th century CE. Remember, all of this is much before the time of Newton. And by the time of 14th century, which is roughly Galileo and Descartes period, and actually a little before even Galileo, they were already looking into two-stage rockets and naval mines. Okay, this is China. Let's look at science in the Indian subcontinent. This is a very, very sporadic thing. There's a lot more. But artificial reservoirs by 3000 BCE, animal-drawn plows were noticed by 2500 BCE. Sushruta, most famously known as the father of surgery in India, was already doing cataract surgery by 6th century BCE. A lot of this is only, I'm not taking corroborative evidence, I've only taken data. Pashmina shawls were noticed and also written about by the 3rd century BCE. We were using carding instruments and we had carding of wool to make fabric by the 2nd century CE. We were using crystallized sugar, which today we know as caramel, by 6th century CE. And by 1366 we were already fighting with firearms, which is the Vijayanagara period was already using firearms. But having stated all of this, having got a sort of an umbrella understanding of where we were through the times, where Western philosophy and Western rational thought was, we come to the man of the hour, Isaac Newton. Born on Christmas Day, 1642 to Hannah Newton. Named on his 12th day after his father. His father had died 3 months prior. He was named on the 12th day because his mother stated that Newton, when he was born, was so fragile that he could fit into a quart jug. So, for those of you who don't know the imperial measures, a quart jug is roughly this size. So, Newton as a baby could fit into a quart jug. They didn't know whether he would survive. So, they waited for 12 days to name him Newton after his father. His father had left him a considerable estate and wealth. So he was born, when he was born, he was already the Lord of Woolstone. Hannah, in the meanwhile, married Barnabas Smith, a local clergyman, who had a big estate in himself and was well off, a 65-year-old man, very vigorous in life. And you can see that by the 3 children that Hannah and Barnabas Smith had in 8 years. So as many historians like to say, and Bertrand Russell says, there was no place for this precocious 2-year-old child in this vigorous marriage. So Newton had to stay with his grandmother. Newton stayed for a long time and ended up leaving home at 12 to join the grammar school in Grantham. Newton was a very, very unique child because he had an intelligence that outstood others, but it came out in spurts. So he would be sardonic, he would be lazy, he would be completely, still he would not move. People thought that he couldn't think because he would endlessly gaze at things. But at certain points he came out with such wisdom that he soon outstripped others. in his spare time that he spent daydreaming, as many people like to call it, he thought of windmills, dolls, furniture, water clocks, and sundials so precise that neighbors in Grantham started referring to time using Isaac's dials. All this when he was 12 years old, mind you. It is very interesting, as I keep talking about it, that the age factor of by when he's completed all of this is a shocker how many ever times I go through this presentation, because Newton breaks the entire thought process of saying this is the growth, this is the developmental spurts that a child needs to go through, because by 12 he's already done things that people at 30 or 40 are thinking about. He's thinking also by 13 on methods to make ink, how to get birds drunk, okay, and how to preserve meat, for which he actually makes a statement. He says, immerse it in a well-stocked vessel under spirits of wine, with a hopeful postscript, from whose taste perhaps it may be freed by water. Okay? He makes his statements, okay, and then he says he has a remedy for the plague. He claims he has a remedy for the plague, and he makes a catalogue of more than 2,000 nouns, okay. Some of his remedy of plague, okay, and it will be really funny, and I don't think any of us can stomach it. Probably we would rather fight the plague than have his remedy. And he says, take a good dose of the powder of ripe ivy berries and add to the aforesaid the juice of horse dung. Okay, and this is his remedy for the plague. What does he say for his nouns? He takes nouns like anguish, apoplexy, bedtick, bodkin, boghouse, statesman, seducer, stoic, skeptic. Okay, by 13 he's using nouns like this. He's got 2,000 of them that he's already catalogued, and then he goes on further to make a phonetic chart of vowel sounds and a table of star positions. These are some, sketches of some of the clocks that Newton did build. Now, the one on the left that you see is actually a picture of the Isaac's dials. In between is the water clock that he made, and on the right is actually a more complicated water clock that he built, where he incorporated a dial into the level of water. Okay. By 16, he had exhausted all that the schoolmaster could teach him. So he decided he was going to come back to Woolsthorpe. His mother said that he's had enough of studies, so she demanded her due and said it was time to come home, begin your life work, your life's purpose, which is to tend sheep and raise grain. So Isaac Newton, as it may be noted, and this is a statement I'm taking directly from Bertrand Russell, and Bertrand Russell quotes, Isaac Newton, I must claim, made a miserable farmer. So he would go to his former landlord's house in Grantham, okay, from Woolsthorpe, for books. He contrived water wheels, dams, and other hydrostatic experiments. His chief delight was to sit under a tree with a book in his hands, and during this time his flock wandered to neighbors' farms and ate all the grain, etc. His former, that is Newton's former teacher, schoolmaster William Stokes, decides that this is a waste of Newton's efforts and Newton's mental faculties and capacities. So he pleads with his mother to send him outside. At this point, his uncle, who is a Cambridge graduate, suggests Cambridge. But there is a big problem that comes up, which is that for people who are born outside Cambridge, there's a £45 tuition fee, a one-time deposit. What we today know as capitation fee is to be paid to Cambridge. Okay? So his schoolmaster says, I will pay the tuition, I will pay the £45. So Newton leaves Woolsthorpe on June 2nd, 1661. And this is a statement I've lifted directly from a book which I think all of you should read, which is called Newton and the Counterfeiter. He says, Newton appeared in front of the officials for scrutiny. The records of the College of the Holy and Undivided Trinity for June 5th, 1661 register that one Isaac Newton has been admitted into its company. Okay? This is the entry that Newton makes into Cambridge. This is an entry that he makes, and one which will last for 35 years. He stayed for 35 years, but you will realize that within the first 3 years, everything that we know of Newton is all done. Okay? So Hannah says, okay, Newton is gone. Newton is also the Lord of Woolsthorpe, which means that he would have lived a lavish life, we assume. But his mother is, Newton still has the problem that he's a minor as we know it. So his mother decided she was going to play the last trump card. And she limited his allowance at the university to £10 a year. Okay? Which meant that Newton could not live the life that many of the more well-off people were doing. So Newton decided that Newton had to enter Cambridge as a subsizar. Now what does a subsizar mean? For those of you who don't know what subsizar means, it means that you are a person who's a peon in your spare time. That is, you work with more well-off students by standing by their side, serving them food, eating the leftovers of what these people left in the plates, emptying the piss pot as they called it, and cleaning it and putting it back, so that you could work for your keep. This is the working for the keep that Newton was doing. However, having done all of this, having entered into Cambridge, okay, the sad part or the surprising part is not one of the students from his years have ever recalled meeting him. In fact, one of them claims saying, I only knew that there was a person called Newton by seeing somebody walking in the distance in Cambridge's big courtyard. Okay? He admitted, okay, and he made copious notes because his mental capacities are so phenomenal. So he starts making notes, and his notes are so wide range because he says he admits to wrongs done to his fellow man in his notes. So what does he do? He says, I stole cherry cob from Edward Storer, and I denied I did so. I robbed my mother's box of plums and sugars and called Dorothy Rose a jade. Okay? So there are things like this, random things that you don't even think that Newton would have done, things that you wouldn't associate with Newton, which he seems to have done. Now, the problem for Newton in Cambridge was that he had one muse, one snare, and that was this absolute thirst and love for knowledge. In between all of this, Newton is said to have also revealed an impressive urge for violence. He said, I punched my sister, I struck many, I wished death on many and hoped it fervently for some. And in a brutal comment on his mother's rematch to Barnabas Smith, he said, I threatened my father and mother to burn them and the house over them. Okay? This was Newton when he was 17 or 18. Okay? This was a person who had immense thirst for knowledge, who had immense propensity for violence and violent thoughts, who had immense wide range. Okay? And in between all of this, this is what he does. He recognized Aristotle as a waste of his time, and he started studying Euclid Geometry. He stumbled upon mechanical philosophy, and he had a legendary capability to study. So one of his co-students said sleep was optional and food was a distraction for Isaac Newton. Wickens, that's what he said. Wickens, who joined 16 months after Newton, said Newton simply did without sleep. Okay? This is just astounds me because it's not human. Okay? How do you ever do this? Okay. But since this was like a more, basic talk for people to understand Newton, I decided to throw in one slide in between so that people understand what Euclid geometry is. So simple, geometry inside circles, things such as the angle subtended by an arc and the opposite arcs are equal. So all of these kind of things which today we learn in class grade 6, 7, 8, 9, etc. are all the things that Newton was actually looking at. He had moved on by the time he was 17. Okay? He discovered it on his own. This was not his topic of study, and he moved on. He discovered mechanical philosophy. Now during this time when he was studying, he said he came up with this work, which since I cannot read the Latin fluently, I am going to go with the English word which is certain philosophical questions in 1664, where he asked very, very basic questions. What is the first and most basic form of matter? Simple, indivisible entities dubbed atoms. Okay? Remember this atom term, Dalton. We have Dalton for the atom term, but simple. He says, what is the true meaning of position? What is location in space? What is time? What is the behavior of celestial bodies? Remember, this is a boy who's still studying in Cambridge, and he's starting to ask these questions. He proved Descartes and coordinate geometry, and he challenged Descartes' theory of light. He studied Descartes' physics and said it was useless. He looked at Descartes' ideas of tides and said, this man does not know what he's talking about. Here is a ranting psychotic. Okay? And this young precocious boy then sought to grasp how the senses work. He was a boy who was going from tides, space, matter to studying how senses work. So what did he do? He purchased a prism. He wrote up his first optical experiments. Okay? Remember the time period. He still not crossed the age of 18. Okay? He studied the motion of why a falling body falls. He's still not grasped this concept called gravity, but he's already starting questions saying, why does a falling body fall? And then he then decides that he wants to test his senses. So he stares at the sun unblinkingly. He takes a bodkin in the eye. What is this bodkin in the eye? I shall talk to you a little later because you will understand it. When you see the image of it, he ponders the nature of air, wondering whether a fire could burn in vacuum. He takes notes on the motions of comets, and he considers the mystery of memory and the strange and paradoxical relationship of the soul to the brain. Okay? That's just simply marvelous and astounding. Okay? Here are pictures. Okay? The bodkin to the eye is actually what I'm talking about in the left. What Newton did was he took a blunt instrument, put it into his eye socket behind his eyeball, and moved it around so that he could change the curvature of the back of his and he wanted to study the pattern of dark and bright spots that he found in his eye. Okay? Now, when asked whether there was pain, he said, I don't know, I just wanted to look at it. Okay? I mean, this is a man I still can't understand.
What age?
He's still not hit 20. He's somewhere around 18 or 19 that he's doing all of this. Okay? And this is his experiment with, this is a drawing that somebody has recopied from Newton's works of his first experiments with prisms and lenses. Okay? And if you see, there are copious notes of A, B, C, D, E, F, G, and all of that. And he says circles, he draws lights, he's got R. It's a scientific drawing as any. Okay? And then he decides, I mean, he has to make his living worth it. So he wrote the Trinity exam to become a scholar. And luckily for him, the College of Cambridge decided to award him the degree of scholarship on April 28, 1664, which meant that he had money to survive, he had a place to stay, and food to fill his stomach. However, in less than a year, the Great Plague of 1665 hits Britain. I mean, it comes on ships, and suddenly there is pandemonium everywhere. Cambridge announces that it is closing its doors for a period of 2 years till the plague closes. But before the plague even hits Cambridge, Newton has left for Woolsthorpe. He sits in seclusion and focuses extremely on mathematics. And this is the period that we know Newton for. What he discovers in his first plague year is the method of fluxions. A lot of us who are not mathematical don't know what this fluxions is. But if the other term that I will define method of fluxions with is something that we will all have heard. It is calculus. So method of fluxions is something that he discovered in the first plague year. Then he comes back to Cambridge in between to say he wants to teach because he's now a scholar, which meant that every 3 terms he was meant to take one course. He was meant to teach one course. Okay? And Newton was said to have actually taken books, underlined random sections, and given it to a student and said, here is your coursework, and was legendarily known to leave the class. Sounds very much like a flute Mali who randomly got up and left. So Newton, it is said, has never taught a proper class. He then returned home because the plague reappeared. He studied how an object moved in a circular path. He said it pushes outward, trying to recede from the center of the circle, okay, which we know as the centrifugal and the centripetal today. He worked out the formula that measures centrifugal force. It's now named, the centrifugal force name is more because of Christian Huygens, another famous scientist of the time. He used a rough estimate for the Earth's size. He calculated the outward acceleration due to the centrifugal force of the earth and what was experienced by man or an object on the surface of the earth. He had an objection to Copernicus' sun system, and he says if it rotates, if it turns on its axis every day as it went, the rotation would generate as much centrifugal force that mankind and everything else on the surface of such an absurdly spinning planet would fly off into the void. This is Newton's statement. And then his attention shifts to the mathematics of gravity. His key idea, it is claimed, came in a blind flash of insight. Why should an apple always descend perpendicularly to the ground? Now, we all know that Newton's apple fell. Today, the tree has been preserved, from which has been the apple tree in the Buildup. But there is a theory that Newton never actually saw an apple fall. He only visualized it. It was just a thought. It was a leap of reason. And he made this statement in a leap of reason and says, matter attracts matter in proportion to the mass contained in each body. The attraction is towards the center of the given mass, and the power, like that we call gravity, extended itself through the universe. Now, does this sound, for those of you who studied a good amount of physics, or at least studied physics till class 10, does this sound like something that we study very often? We know it by his name, just FYI. This is the beginnings of what we know today as Newton's universal law of gravitation. Objects attract each other with the inverse square of the distance and directly proportional to their masses. And they attract towards the center of each of the objects. Okay? This is sort of the smidge of the seed of the idea that the universal law of gravitation begins with. And today, many people claim that apple is the most significant apple ever since Eve had the mythical apple. Now, the statement that they make, and sometime during the summer of 1666, I found myself in the garden of Buildup sitting in the contemplative mood, or perhaps he recalled this moment decades later. In my mind, the apple tree of my childhood was heavy with fruit. An apple fell. It caught my attention. This was Newton's words. Okay? We do not know whether these words came immediately following this apple or whether it came decades later, but essentially this is the idea that we all associate with gravity. The simple apple fall that we all know Newton for, I don't know where the ladder came in, but anyway, it is. But anyway, this is a picture that we know very famously for Newton. He calculated Earth's gravity using experiments with pendulum. He did a very strange connection which not many of us use, which he said gravity is 3,000 times the centripetal force of Earth. Okay? I do not know why he came up with this mathematical connection, but anyway, he did this calculation. He did a problem with the Earth and Moon and the gravity of them and them pulling each other and objects all around them. And from Kepler's third law, he comes with the inverse square law, which is the force which keeps the planet in their orbs must be reciprocally as the squares of the distances from the centers around which they revolve. Now, as we move on, he redefines the most basic concepts of matter and motions. His definition by 1666, is this is known please read ye as the, ye as the. It is known by the light of nature, the equal forces shall affect an equal change in equal bodies, for in losing or getting the same quantity of motion, a body suffers the same quantity of mutation of its state. Okay? This is as scientific as you can get in language. Okay? This is finding the needle in the haystack and then searching for the eye of the needle. But he then also goes on to define that the change in the motion of a body is proportional to the amount of force impressed on it, okay, which is roughly the second law of Newton's motion. And 20 years later, all of this which we have forms the laws of motion as we know it. He then went on to studies of light, its color and optics, something he started when he was in Cambridge. In 1667, he returns to his rooms in Trinity College after 2 years. All of this Okay? In the interval, he has become the greatest mathematician in the world and equal to any natural philosopher then living. And then Newton does the biggest thing. He turns 24. In 1669, at the age of 26, his former teacher, Isaac Barrow, resigned, and Newton becomes a Lucasian professor of mathematics. He is required to deliver one course every 3 terms now as a Lucasian professor of mathematics. Year after year, he published next to nothing for the next 15 years. So, by 24, Newton is the greatest mathematician and the greatest scientist we know of, and for the next 15 years, Newton sits like an idle duck. Okay? This is a man that we know who changed physics and who changed mechanics as we know it today. Now comes a turning point. Edmund Halley, another famous person whom we know for the Halley's Comet, visits Newton in 1684. He says Robert Hooke, another famous scientist, Christopher Wren and Halley have a bet on whether the inverse square law applies. Hooke claims that I have a solution which Wren and Halley doubt. Wren then offers a reward of 40 shillings saying, if there is a proof, then I shall give this 40 shillings. If somebody can prove and tell me what is Hooke's proof. Here is Edmund Halley. Halley puts a question to Newton. There's a long question which he puts where he says what he thought the curve would be that would be described by the planets, supposing the force of attraction towards the sun to be reciprocal to the square of the distance from it. Okay? And then Newton says, I solved the problem some time ago. And Newton immediately replied that it would be an ellipse. Halley, struck with joy and amazement, asked how he could be so sure, and Newton replied, why, I have already calculated it. So Halley says, I want it. I want to see what it is. And Newton says, I can't find it. So what does Newton do? He does the next best thing. He rewrites it. So Newton tries to recreate it and makes a mistake in the geometry in the first place.
Sorry, there's a slightly different version elsewhere, where apparently Newton knew that he had made some mistakes. He knew the rough answer, but there are some mistakes, and he didn't want to show Halley the one with the mistakes. Then eventually
so there are different theories. There are certain theories which say that Newton had the paper on him and he also was ready to give it to Halley, but then he decided, why should I do this because I've already figured it out. There are certain places where he said, I'm in the ballpark area, which as you said, and therefore I do not want to show my work outside. Be that as it may, the basic understanding that everybody takes for granted is that Newton rewrote the paper and then he corrects all the errors, and by November he works it out, but this time using a very different branch of mathematics called conic sections. So what comes out is de motu corporum in gyrum, or on the motion of bodies in orbit. It's a 9-page manuscript. Halley looks at it and grasps the significance, and he says this is the foundation of a revolution in the entire science of motion. So Halley immediately takes Newton along with him to the Royal Society and says, please present it. The Royal Society says, wow, you've come up with something, okay? This is not enough, you want to understand more. So the Royal Society says, go ahead, we will publish it for you, please create a revised version. So Newton puts off the publication for 1.5 years, and then later, 1.5 years, almost 2 years later, he sends Halley an expanded treatise of the first 2 parts. It becomes 2 parts, okay? And then he attempts to create a new science called rational mechanics. And these 2 parts brings us to Philosophiae Naturalis Principia Mathematica, or the natural principles of philosophy, as he likes to call, as people interpret it, or the principles of natural philosophy. People interpret it either way.
Mathematical principles of natural philosophy.
Huh?
Mathematical principles of natural
Correct.
philosophy.
But many people work it wrong, but it is actually the mathematical principles of natural philosophy. In fact, for those of you who are really interested, there's a man called Florian Capari who, really long ago, has completely translated the entire 3 volumes of Principia. It is available in English. If some of you would like it after this, I have the PDFs, you can take it from me. Astounding work. A lot of the English sections, in fact every part of the Principia I have taken is from that. It is considered one of the most important works in the history of science. The famous book of Mathematical Principles of Natural Philosophy marked an epoch of a great revolution in physics. The method followed by his illustrious author Sir Newton spread the light of mathematics on a science which up to then had remained in the darkness of conjectures and hypotheses, said Alexis Clairaut. The Principia begins with definition and axioms. The axioms that he claims, by the way, it's just 3 pages with 10 corollaries. The axioms that he's written in the beginning of the first book is actually what we know today as Newton's 3 laws of motion. And this continues into 3 books. I have the actual introduction to Principia Mathematica as made by Newton himself, because in the forward to the first, book, the forward to the first edition, Newton actually makes a lovely presentation. Let's hear from the man himself. So this is actually Newton's introduction to the first edition of the Principia Mathematica, which today has been brought to us by the amazing technology we know as text-to-speech. So I have taken the PDF and I have converted it through text-to-speech using a person called Harry, who's of a British origin, so that we get something that sounds deep, baritone and closest to the English language as possible. But since it is a computer, please do forgive the small little glitches in audio.
Since the ancients esteemed the science of mechanics of greatest importance in the investigation of natural things, and the moderns, rejecting substantial forms and occult qualities, have endeavored to subject the phenomena of nature to the laws of mathematics, I have in this treatise cultivated mathematics as far as it relates to philosophy. But I consider philosophy rather than arts, and write not concerning manual but natural powers, and consider chiefly those things which relate to gravity, levity, elastic force, the resistance of fluids, and the like forces, whether attractive or impulsive, and therefore I offer this work as the mathematical principles of philosophy, for the whole burden of philosophy seems to consist in this: from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena, and to this end the general propositions in the first and second books are directed. In the third book I give an example of this in the explication of the system of the world, for by the propositions mathematically demonstrated in the former books, in the third I derive from the celestial phenomena the forces of gravity with which bodies tend to the sun and the several planets. Then from these forces, by other propositions which are also mathematical, I deduce the motions of the planets, the comets, the moon, and the sea. In the publication of this work the most acute and universally learned Mr. Edmund Halley not only assisted me in correcting the errors of the press and preparing the geometrical figures, but it was through his solicitations that it came to be published, for when he had obtained of me my demonstrations of the figure of the celestial orbits, he continually pressed me to communicate the same to the Royal Society, who afterwards, by their kind encouragement and entreaties, engaged me to think of publishing them. But after I had begun to consider the inequalities of the lunar motions, and had entered upon some other things relating to the laws and measures of gravity and other forces, and the figures that would be described by bodies attracted according to given laws, and the motion of several bodies moving among themselves, the motion of bodies in resisting mediums, the forces, densities, and motions of mediums, the orbits of the comets, and such like, I deferred that publication till I had made a search into those matters, and could put forth the whole together. Some things, found out after the rest, I chose to insert in places less suitable, rather than change the number of the propositions and the citations. I heartily beg that what I have here done may be read with forbearance, and that my labors in a subject so difficult may be examined, not so much with a view to censure, as to remedy their defects.
This is actually not the entire forward, but I've taken the relevant sections, because there are sections where he says, I did not want to publish this until I have got to the bottom of this. he in fact says, don't look at my book for censure, but to remedy the defects. Okay? Here is a man who is putting caveats even before he started. Isaac Newton says, look at my book to remedy its defects. Okay? And that's what many post-Newtonian scientists have done. But looking at the vast subjects that he covers, elasticity, levity, gravity, etc., this is a book that actually I would think that every school child should at one point at least glance through. So he starts with definitions. The book, the Principia Mathematica, which is called Liber Primus, the first book, starts with what is called definitions. He just calls it definitions. And the kind of definitions he uses, it says the quantity of matter is the measure of the same arising from its density and bulk conjointly. Okay? Now, to understand this definition itself, you need to understand where he comes from. Each of these definitions is a talk in itself. So I would not want to go into this because I did happen to go to Professor, why do I forget his name? Anyway, a very senior physics professor in the Institute of Mathematical Sciences. And on this slide alone, I had a 1.5 hour lecture, and he said, okay, I finished the first definition. And that's how detailed each of them are. And look at the detail of his definitions. He says the quantity of motion is the measure of the same arising from the velocity and quantity of matter conjointly. What he's trying to do here is he's trying to define matter, he's trying to define time, he's trying to define all of the factors. I've only taken the first 3 definitions. He's trying to define everything before he says, okay, now let us proceed and let us study properties. And then he makes amazing statements. He moves on to what is known as an axioms. It follows the definitions. Today we know them as the 3 laws of motion. This is the Latin version of it. Therefore, for those of you, including me, who cannot read Latin, for those of you who can read Latin, please raise your hand and you can read it for us. But for the others, I have taken Florian Caperi's translation of the same. He says, everybody continues in its state of rest or of uniform motion in a right line. Okay? He doesn't use the word straight line, he uses the word right line, unless it is compelled to change that state by a force impressed upon it. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which the force is impressed. Okay? This is as technical as you can get to define the laws of motion. To every action there is always opposed and equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed to contrary parts. He doesn't even say towards each other, he says to contrary parts. In fact, some of the definitions and some of the statements that Newton makes are so precise, because to define certain things, which you will see in a few slides later, he uses mathematical numbers to define certain physical phenomena. Okay? Some things that we do not even look at. So let's move on. By the way, a lot of these pictures, in fact including this from here onwards, are taken from a 1723 version, the Latin version of the Principia Mathematica, which today is available. Actually, the exact copy today is in the Madras Literary Society, which Mr. Gopu had spoken about. So I am going to be using a lot of this because I wanted to take from the original. So what is that? It's called De Motor Corporum Liber Primus, or On the Motion of Bodies, the first book. It's the first volume on the motion of bodies. It concerns the motion in the absence of any resisting medium. It opens with a mathematical exposition of the first method of first and last ratios, which is the geometrical form of infinitesimal calculus. I have a lot of notes here which I'm not going to get into, but this is how he starts off. This is section 1, okay? Post the definitions and his other axioms, he gets into a first definition, and then section 1, where he says de methodo ratio. So he starts with the ratio of things, okay? And all of them are given as lemmas. Lemmas are the major topics, you can call them headings, under which he will give you he'll give you a propositio, which is the proposition, under which he will give you a corollary. So it is actually a very, very, very divided, very, very algorithmic, very, very sequential form of division in this book. Here he takes conic sections, he takes ellipses, he takes geometry, he takes movements, he takes pendulums, he takes time, everything. I mean, and it's a motion of bodies. So as long as there's no resisting medium, this book has it. So here he's talking about what do you say? It's one of the motions. So he says in this figure, he's talking about a certain motion. Okay. To understand this better, I could have explained this, but I chose not to because I just wanted to show you an idea of what it is. Now, if you look at this is a proposition which I've taken in Latin, but I would like you to try and figure out. I've shown you some part of Latin. Try and figure out what this might be. So,
see, quadrato distantia as square of the distance.
So there you've already had it. Quadrato distantia and also spherum, corpusculum, and he uses quadrato distantia and he says centro. Okay, that is good enough for you to realize that this is Newton's universal law of gravitation. That a particle attracts every other particle in the universe using a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This was first tested by Henry Cavendish 111 years after the publication of the Principia. Okay, so for 111 years this was taken as the word of God. Okay, and you will realize that there is somebody who is going to quote and say there is no mortal who can reach the heights that Newton is God. Okay, and we shall see that. Okay, and 111 years after publication of Principia meant that 71 years had passed since Newton had died. Okay. Now, I have given you something to identify. Now try this.
Revolution. Elliptical revolution something.
Okay, so I've given you three propositions.
Okay.
Two propositions and one corollary. But the fact that I've given you three should already give you a clue.
Kepler.
Great. This is Kepler. Okay, this is his statement of Kepler's laws. Okay, but what I meant by mathematical is if you actually see here it is in this can you see this? It's actually if you read it properly it is sesquiplicata. Sesquiplicata means 1/16th. He uses 1/16th to define time period here. Okay, he uses 1/16th. I was unable to get the exact thing because even Florian Capri translates it and gives you only the law that he's given. But the sesquiplicata was actually explained to me again by this professor at IMSC. Anyway, I will give you the name hopefully if it strikes me at the end. But again, this is again the page, the first page of the English translation by Florian Capri, so that you see what are the things he's covered. First and last ratios, centripetal forces, eccentric conic sections, ellipse, parabolic, hyperbolic orbits. Okay, and it goes on. Okay, this is first side, and then you go there to the second one. Okay, and then he goes to De Motu Corporum Liberus Secundus, which means the second book. Now, why does he continue to call it De Motu Corporum? Because Newton says part of the contents were originally planned for the first book. Okay, but I decided to include them along with motion through resisting mediums. So there are different conceivable laws when resistive mediums come in, and he says largely I wrote this to refute the theory of Descartes, because Descartes had this theory called the theory of vortices, that is, objects moved because a certain flux of vortex kept planetary motion going on. And a lot of this flux theory and vortices etc. he wanted to refute, and which is why he wrote a lot of this on resisting mediums as a separate section itself. And which is why he says, I've quoted Descartes there, which says, whirling fluid of vortices filled interplanetary space and carried the planets among them. Descartes in fact was building on Kepler, who said that there is a polyhedral structure for the universe, which he first started with a polygonal. It's an entire flat geometric structure which Descartes decided to build upon. And now Newton said, I'm going to refute all of them in this one statement, one section of book. So he says, Newton says the hypothesis of vortices was completely at odds with astronomical phenomena, and actually it does not serve as much to explain as to confuse. Therefore, what does he do? He starts off with saying, what is the definition of fluid? A fluid is a body whose parts yield to any force impressed on it by yielding as easily moved among themselves. Okay? This is a definition that you have to do a lot of introspection, because he uses saying easily moved among themselves, and he uses like a interloop, and you will see a lot of these statements where he loops back onto his own definition on themselves, etc. He uses he defines pendulous bodies. He says are resisted in the ratio of velocity and have their oscillations in a cycloid isochronal. Okay, these are terms that are ready to scare any person other than the rabid physicist to get away from that subject altogether. So there are, and the definitions go on. Propositions.
What is that cycloid?
Cycloid isochronal is a very specific thing.
I know it is specific.
There is cycloid is a shape.
Correct.
Where a body moves from any one point to another point. It takes whatever the starting point and whatever the ending point is. The time taken is the same.
Correct.
So
But I'm saying, I understand that, but I'm saying, when you read a definition saying cycloid isochronal, it is ready to scare everybody. Okay? If you're going to say it will take the same time from moving from point A to point B, then the school student is ready to understand. Which is why it takes a lot of effort, and it takes immense amount of brain power to try and read through even Florian Capri's translation, because there are terms like sesquiplicata where he says 1/16. So you're trying to figure out what 1/16 is. You're trying to figure out why he's using cycloid isochronal here. What is he trying to say? Okay, if you move on, he says rare medium consisting of equal particles freely disposed at equal distances from each other, a globe and cylinder. So he's describing geometric objects, okay, moving through fluids. Okay, so there is a very, very indivisible line between this mathematics, between geometry, between motion, between fluids. There are multiple fields that each of them looked at as separately. Fluid mechanics, strength of materials, geometry, etc. are sort of very fluidly moving among each other. Specifically looking at the way that Newton proceeds in this book, he will have the motion of a pendulum, he will then move on to motion of objects, and therefore it is an amazing study of the limits of human capability in terms of staying with an object and reading boring stuff, if you want to call it that. But it is outstanding in its vast range that it covers. Okay, this is still, moving on to book 2 where he says, this is still book 2 where he says bodies that are resisted as a square of their velocities, bodies that are resisted in the ratio of their velocity, and he's going on to circular motion of bodies, motion and resistance of pendulous bodies, motion propagated through fluids, circular motion of fluids. He's not going only to properties of fluids, he's also looking at the medium, the resisting medium itself. It is such detail that actually makes the Principia the go-to book for anyone who wants to look at classical mechanics. Then of course he says De Mundi Systemae Liber Tertius. Here he says on the system of the world. And there he decides to give an exposition of the many consequences of universal gravitation. He said, so Newton claims, I've looked at the small, at the micro, I'm now going to start looking at the macro. I'm going to start looking at the motion of comets. I'm going to start looking at the features and irregularities, including orbital motion of the moon, variations in that. What are built on the propositions. So as he says, I wrote some propositions, but I had a few findings later. So I didn't want to change the propositions, therefore I added it much later. So therefore the book 3, which is the system of the world, has a lot of propositions that actually go better with previous volume 1 or volume 2, but is put in here because he did not want to disrupt the flow of volume 1 and volume 2. He looks at the heliocentric view of the solar system, the deviation of the sun from the center of gravity of the solar system. This is, some serious talk. He's looked at the macro, and in as much detail, if not more, than the detail in which he's looked at the micro, including objects, including geometry, including the mathematics, including infinitesimal calculus. There is a range to which a man can actually study. Okay, and this man has done it. So, again, I've taken a few sections from, again, book 3, where he says the force by which the moon is retained in its orbit tends to the earth and is reciprocally as square of the distance of its place from the earth's center. Universal law of gravitation, reframed, but in terms of between two bodies specific to the earth and moon, because he was actually doing what is called the earth and moon problem in trying to find variations and irregularities. The flux and reflux of the sea arise from the actions of the sun and the moon. Here he is talking about tides with reference to astronomical bodies and gravitation that comes along with these astronomical bodies. Now he's looking at comets, okay, to talk about the different kind which he threw in between. I've thrown in a lemma 5 to find a curved line of the parabolic kind which shall pass through any given number of points. Okay, is something that comes in book 3. And you are really stumped as to how it fits in with comets and sun and moon and tides. But essentially, when you listen to what Newton says in his preface to the first edition, you understand that he had a reason for it. Again, this is what he covers. He covers the rules of reasoning in philosophy, phenomena, propositions, motion of the moon's nodes, and general scholium. Okay. Now, what was the praise for the Principia? Principia came out, and Acta Eridot said it is an investigation so worthy of so great a mathematician. Okay, so they're saying Principia was actually only Newton could have had it, and it actually gives us the worth of what Newton is. It is not possible to make demonstrations more precise than which Newton gives. And who said this? Cartesian. Okay, Cartesian, who was a scientist, a mathematician of such caliber, makes statements like this. I can go on and on, but more importantly, I'd like to quote Marquis de L'Hospital, as we all know him as L'Hospital's rule that we learn in mathematics. He says, "Good God, what fund of knowledge there is that in that book. Is he like other men?" Okay, this I think summarizes Newton in all that is. Okay, and coming from a peer of such standing, it tells us who Newton was. Okay, and so if we think Newton was this blip and it all ended, we had Euler, Lagrange and Hamilton among the greats who followed. Leonhard Euler from Switzerland actually did discoveries in infinitesimal calculus and graph theory, worked in fluid mechanics, worked in dynamics, astronomy, music. Euler-Bernoulli beam equations. Euler's equations are most known for fluid flow, and a lot of we know Euler equations with a lot of mathematical forms. But I'm saying, Euler himself says it is on Newton that I built. Okay, for all the fallacies, the flaws, the gaps that Newton had, we had Joseph Louis Lagrange who came in, and he actually made contributions to number theory, classical and celestial mechanics. He reformulated Newton's mechanics and made it Lagrangian mechanics. He changed force and used the word potential in that place. Then we had Hamilton, Sir William Rowan Hamilton, who made contributions of immense nature to classical mechanics. Today we know it as Hamiltonian mechanics. And all of this comes up. Okay? And in between all of this, like many authors say, in the time that this book went to publication, this happened. Okay? And in the time that this presentation was going into publication, this is what came up in some posts. Manchester University confirms. This is how Isaac Newton stole the concept of gravity from a Hindu Gurukul. Ashish Sharma is the name of this author. It comes up in something called mensonfiles.com. I don't even know where this came up, but I decided I'll throw it in for just the magic of it, because it says Rishi Kannada of the Vaisheshika Darshanam was a Vedic nuclear scientist, and Isaac Newton stole all his ideas from him. Okay? Well, I know of at least 10 other people who would say Jai Ho and go, holding flags to this, but I do not want to get there. I just wanted to throw this in as a spin because after such heavy Principia, I decided it will be interesting to see what are the kind of things that Newton leads to. Okay? So, Dr. John Verghese Joseph of the University of Manchester says the Kerala school identified infinite series in 1350. So, pi series is there, it was calculated to 9, 10 and 17 decimal places. Strong circumstantial evidence that it was passed through knowledgeable mathematical Jesuits who then passed it on to Newton himself. Then the brilliance of Newton's work stands undiminished, but especially, with calculus. But you need Madhava and Nilakanta of the Kerala school to stand shoulder to shoulder with him because they found infinite series too. Okay, I'm not supporting this, I'm not refuting this. But here is a man from Kerala, George Verghese Joseph, who is from the University of Manchester, who is claiming this. Okay, he says in his book, which is the crest or the peak of the non-European roots of mathematics. Princeton University Press is publishing this, by the way. But for some unfathomable reason, the standard of evidence required to claim transmission of knowledge from east to west is greater than the standard of evidence required for the knowledge to transfer from west to east. Okay?
I have this on both books, this one and...
I know, but I'm saying, but what actually really hit everybody was this one picture. Newton versus Rishi Kanad, and the line below that, thief Newton copied Rishi. Okay, that's what hit me the strongest. Okay, it was funny because they have first law of motion, they have Kanad in Sanskrit, and then they say Newton's law. Okay, all of this is great, it is funny, but in the study of classical mechanics and in the epochal changes that came to classical physics, to mathematics, and the study of our world itself, Newton stands undiminished, and which can easily be given because I would like to actually show you that Halley, okay, wrote this in Latin, okay, and this, I think, is the true standing testimony of what Newton is for us today, okay. For all of this, it goes on saying the sun and the moon, the earth, the flowering plants, it's a whole ode, it's a paean to universe and the creator. But he ends it with this one paragraph which I translate. Then ye who now on heavenly nectar fare, come celebrate with me in song the name of Newton to the muses dear, for he unlocked the hidden treasuries of truth. So richly through his mind had Phobos cast the radiance of his own divinity. Nearer the gods no mortal may approach. And I think for me and for today, I would like to end with that statement. Nearer the gods no mortal may approach. Thank you. Would you have any questions?
Newton, I think, to sort of systematize the whole thing and create a framework to study this, and also use significant amount of mathematics to describe whatever it is that he is saying. That is why he's fresh. I mean, this is where the mathematical physics effectively starts. Because I don't believe before that, be it Galileo or people have done. They have tried to, Kepler, for example, put together all the data and then figured out that it is actually an elliptical orbit. But to completely define a set of rules, move it to the space of equations, and then do enough calculations to show that this is how things work, starts with Newton. And that's the real greatness.
Well, yes, I agree with you. In fact, which is why I am showing you the amount of derivations, the diagrams that he did in the Principia. The scientific rigor, the way he formulated things. Earlier you had logic, you had philosophy. He continues to say the mathematical principles of natural philosophy. But his work is anything but philosophy today. It is scientific rigor, backed by mathematics. And Newton himself claims, I had all these results, but I did not want to go into publication until I got to the bottom of it. Okay? Now, I have only stopped with where the Principia ends. Okay? If you actually read the book, Newton and the Counterfeiter, you realize, okay, and not many of us know, that Newton had a second career, where he became the guardian of the Royal Mint, and he went after counterfeiters with the same rigor as he put into science. Okay? He created methods, he creates checks, he creates everything that actually confirms even some of the greatest minds. Okay? And that is what I am saying. Newton's, the process, the flow, the strength of his mathematics that actually pervades every one of his statements is, I think, what changes the epoch of physics and our understanding of science from, of course, the previous giants. Yes. Well, I'm a little scared to answer questions.
No. I mean, do you know anywhere did ever Newton mention any drawbacks of his own laws or his work?
Newton, does he mention drawbacks? Well, he does say in the preface to the second edition, he does say, I have made a few corrections, I have made a few changes, though you do not know what the drawback is.
Okay, maybe to be more precise, let me say that the universal law of gravitation.
Correct.
For example, it says that when you move these two bodies,
Correct.
the something is changing instantaneously, which means if the distance is zero, force becomes infinity.
Correct.
Or if you are moving it close together or apart from each other, something is moving, or the force here, what he called it as, changes instantaneously, which means at infinite speed.
Correct.
Which actually made Einstein to reformulate the law of gravitation and so on.
Understood.
So I'm curious, did he ever mention about his own drawbacks in his own book, in his own work? Because I have never read
As
this.
far as I've seen, okay, and as far as I've read, I can be very honest, I've read a fairly good portion of the Principia, but as far as I've seen, the only place where he mentions that there exist drawbacks have been his prefaces. He says, because even in the preface to the first, he says, in the laws of the moon, etc., I have found a few changes which I have corrected and I have incorporated in the end without changing the propositions. So he talks about the fact that he realizes there are problems, but unfortunately, I don't know, but through his book, through the crux and the entire chapters of the book, you do not see the mention of saying, here I was erroneous. He only gives you the corrected results which move on. So I think only with comparison between the first edition and the second edition that maybe one might be able to see where the errors were. But he does not specifically say, I made errors here. He says, I made errors in this area.
Also, as you said, he said that it's been offered for review and correction.
See, that was very clear, because Newton said, I want people to read my book with a critical eye so that they might correct the things that I have made mistakes in. That is clear. So he knows he's made mistakes. We also know that he made mistakes from the beginning.
In this case, I don't think he made any, as far as this particular framework is concerned, the question that he's raising is something more profound, which is when these activities, that is the force experienced by a body,
Correct.
when you make a small change in another object, is instantaneous.
Understood.
So that idea is something that is that became problematic only much later. Until Einstein started thinking about it, nobody even thought about it. The most practical problem that people had was Mercury's orbit, precession of Mercury's orbit, which is what they couldn't figure out. And Newton also probably knew that there were some problems with the calculation.
So that's what I was curious about.
No,
Other than that,
he did know about it, but to answer your question, to find a flaw in the basic law of universal law of gravitation, okay, we had the statement of Newton, okay, and then we had 111 years before Henry Cavendish tested it. Okay?
You see that Newton have not derived this law. He formulated it.
He merely stated it.
He stated it, correct.
These laws.
Correct. And he gave a mathematical backing to it.
By getting the insights from the Kepler's law, he formulated
Correct,
it.
and he gives some mathematical calculation to it also, because there are certain sections, in fact, in the book 3, that he talks about the motion of bodies, how the Earth and Moon, he goes into a lot more detail there. But there are definitely, if you look at it as a physicist and with somebody with a scientific eye, you know there are mistakes. But Newton himself did not claim that I have made a mistake there, if that answers your question. He's not made an explicit statement of a mistake or a correction in a particular segment. He just blanket says.
I think if you recognize the mistake, you would have stumbled upon relativity.
Yeah, exactly.
It's blind.
Exactly.
You know, it's like saying, what did Newton say about oxygen or chemistry? It is completely beyond his imagination.
Beyond his imagination, absolutely.
So it's beyond the state of imagination of the world scientific
At that
method.
particular time, yeah. I don't think he did any mistake. It was just a.
No, he says I did make some mistake in geometry,
That was
etc.
probably more in calculations or some.
Correct. Those mistakes is what he talks about. He talks.
But this is more physical. It's
No,
not
no,
a
this
matter
is-
of calculations.
Well, I agree here and say I don't think Newton even realized this was probably a problem.
So like he said, I think he tried to construct a model, a set of equations based on the model to actually do that. And where it breaks, where it works, I think
See-
broadly it worked everywhere. And where
Yeah.
it breaks,
No, but the thing is the microcosmic thought I don't think is actually something that Newton specifically went into those extraneous cases, number one. Number two, I think Newton's strength was not about the statement of the law itself, but the mathematics that he used to back that. That he says, I'm not making a statement alone. Here I have given you numbers and data that says, yes, this is where my law is. Okay? He does not use two objects and measure, but he uses conic sections, etc. to prove it. He uses geometry, but he anyway goes into that.
It may not be in this sense, but I think I've read somewhere that Newton did something which helped disprove one of his own theories. Because Newton's theory of optics was the corpuscular theory of light. And he actually did an experiment called Newton's rings, which actually supported Huygens' wave theory. But there was this dilemma where he was wondering whether he should publish it or not, because publishing it would go break his own theory. But he went ahead and did it anyways. So maybe that was an example of where Newton did something knowing that it would actually break one of his own theories.
But certainly, his theory of optics is certainly flawed.
But
Actually, it came back again, De Broglie. In fact, one of the books where I read it, it had...
No, that's just the concept. But in terms of
Let me.
okay.
So this is getting into discussion rather than any questions to the lecture.
Sorry.
So let's close it and we can have a discussion. So very nice to have a discussion, which is what we want to encourage. But as far as the lecture is concerned, we should just deal with questions on the lecture and then have discussions outside it rather than as part of the lecture. I'm glad, even though in a kind of a mocking or a humorous context, he brought in Kanada and Vaisheshika and so on. That's a totally different system of thought a long time back. The reason this kind of fake or distorted version of history comes through is because generally there's nobody to talk to us about it. Your mathematical books talk about Newton, Siddharth talked about the inspirations. Aristotle, Euclid, Galileo, Tycho Brahe and all these people. What number system was Isaac Newton using? The Indian number system. Who came up with that? Brahmagupta's formulation is something that should be there in every textbook, and it's not. If it's not here in India, of course there people are going to come up writing stuff like Kanad's, Vaisheshika and stuff. Why is Brahmagupta not there? The earliest mathematics that you are studying in any school, 2nd standard, 3rd standard, is Brahmagupta's mathematics. It's not there. If it's not there in Indian books, how is the world going to know? He didn't steal that. He didn't have to steal anything. But he was borrowing and using a lot of Indian mathematics. That is not expressed. So one of the things that we want to do is also talk about not just confined. So I'm glad he had 3 slides where he talks about European mathematics, Chinese science and Indian science, because that tends to generally get neglected. So I'm glad he did that, and we'll get some of that also later on. I would like to add one little piece of trivia and then I'll close it with it. Newton's work was in Latin. He was an Englishman living in England and he didn't write in English. He wrote it in Latin. He had to wait for English translation. I don't know if that was the first translation, but the first translation into a language other than Latin was in English. The second translation was into French, I think a few years afterwards. Do you know what the third translation was? Which language the third translation was and by whom?
Don't tell me it is Sanskrit.
Huh? No. You would not. So both the language and the location would be surprising as hell. It was in Persian by a man called Tafasul Khan who lived in Allahabad. So that before the Russian and the German translations, if I am right. And this is something that is mentioned in the Asiatic societies, some of the proceedings. So, absolutely fascinating stuff. And that Tafazul Khan was a contemporary of William Jones, and then there's a whole other connection that goes there. So, astounding stuff. We know nothing about Tafazul Khan, almost next to nothing about Tafazul Khan. And so, this is the kind of thing we want to bring out. Do any Indians know that Newton was translated into Persian by an Indian? Nobody's done it in Persia. But not into Sanskrit, which has a very long tradition of mathematics in India. Think about that. So these are the interesting things that we hope we'll find out, and we as our lectures go through the year, and hopefully will continue for several years, some of those aspects also will come out. Not just the familiar names mostly of Western scientists, but also of unfamiliar names of even Indian scientists. So thank you all for coming, and I hope to see you next month.